I'm going to draw the DME column, and I'm going to basically follow my instructions that are on the wiki, but I will kind of throw a caveat out at you. I started doing a little bit of research on distillation columns last night, and I've been doing this kind of the same method of control for a bunch of years. And suddenly, as I'm starting to dig through some of the more practical literature, I'm finding a lot of really interesting examples of different ways to control column pressure. So I put a couple of links on the wiki just yesterday. I worked pretty hard yesterday, actually, reading, trying to absorb as much as I possibly could. And so I've got a couple of links on the wiki. Maybe I'll just show you what they are, just so you can have a heads up on this. Let's just pull this up. And so you'll find this link on the wiki right now. And it's an article from a magazine called Chemical Engineering Progress. And if you've never had a chance to kind of peruse through the library, Chemical Engineering Progress is one of those really, really great journals with really practical engineering, chemical engineering stuff in it. There's also Chemical Engineering Magazine as well that's extremely practical as well. But what's nice about this one is it just goes through a whole bunch of different control schemes for controlling columns. So I may take a stab at trying to use one of these control schemes because it comes highly recommended. In addition to that one, there is, let me just, there we go. If you find the control scheme, I've put 3 links on the wiki yesterday. So one of them is a book by Lubin, who's a prof down in the States, and also Buckley, who's a really, really experienced DuPont distillation designer. And so I would recommend you have a look at that book. I was flipping through a technical article that Buckley had written, and it was really helpful for me. And then the next one down is, some of the stuff is pretty old, eh? Look at 1985. The other one is a guy named James Riggs, who seems to have incorporated a lot of Buckley's information around distillation column control. So it's quite good as well. They're fairly long articles, actually. So I'm not sure how much you're really going to absorb, but you might want to just grab a copy of them and stick them in your files somewhere. Okay, so let's go back to the simulation here. Before we really do a lot with this simulation, you really need to know what the equipment is going to look like. And that is partially, the performance is kind of partially defined by the simulation that we have there. And the first thing that's recommended is you make sure your model is using actual trays with actual efficiencies rather than 100% efficiency and ideal stages. So what I did is I took the information that came from Mike Croa, which essentially built up their methodology. The paper that he sent us recalculates for every 100% efficient stage, so every ideal stage, he calculates the number of transfer units that's required to do that with packing. And I just really took the inverse of that to work out essentially a stage efficiency. And so I created a bunch of stage efficiencies through the tower like this. And then we know that we need more than 10 stages. So what I did here is basically kind of prorated those into the, I took the average, which is about 0.6 tray efficiency, and then just kind of prorated my calculated efficiencies from his number of transfer units into a bunch of stage efficiencies here, just to give me a little bit better sense of what the temperatures are through the tower. So hopefully that'll be a little bit helpful as I'm going through it. And how I do that is, sorry, the screen's a little bit small, so I just kind of scroll back and forth here. what you do is you go to the parameters page and then go to efficiencies, and then you can put your stage efficiencies in there. So once I calculate in a spreadsheet, I just copy and pasted it right in. You could probably get away with, if we're just assuming a 60% tray efficiency, you could probably get away with just putting that right the way down. But that was the way I did it. Okay. So that just gives me a little bit different profile in terms of the temperatures through the tower. And I also added a couple of specs just so I could check some of the sensitivity of compositions to condenser temperature and reboiler temperature, and also the various flow rates in there. So you can see I've still got all the composition specs in there, but when I started playing around with this a little bit, I was switching back and forth between the specs just to get a sense of how sensitive the temperatures are to different compositions at the top of the tower. I could kind of see this coming. And we haven't had this problem very often in our 470 tower, but we've got these really flat temperature profiles in this tower, and I think it's going to make it really challenging to try and control this. So I wanted to see what different compositions at the top of the tower would do to the different temperatures, and see if we could actually measure a different temperature at the top of the tower based on if the composition was varying. So what I did is I just tried a couple different cases. I copied those numbers into a spreadsheet. So right there, this is the base case here, and these are the specs. So there's the reflux ratio, there's the reflux rate there, there's the concentrations that we were trying to achieve, and there's the various temperatures there. And what I did is I just backed off on the methanol composition just to see what would happen to the condenser temperature, and I went down by a very small number, and basically the temperature wasn't varying very much. So it's down sort of in the 4th decimal place of temperatures. And then I did a little research on temperature accuracy, and I used I'm going to talk to one of my instrumentation friends and just sort this out, but one thing that I found was if you use an RTD versus a thermocouple, so a resistive temperature device versus a thermocouple, you can get slightly better accuracy, and also you get better repeatability. So even if you don't have the exact temperature, you at least come back to when it's measuring at temperature and it's the same temperature as before, it measures the same value. So a good RTD is only accurate to like 0.15 degrees Celsius, and all the way as I'm changing the concentrations and the top of that tower, upping or decreasing the methanol concentration, basically the temperatures are not changing by more than 0.15. So that's, I think, going to create a few problems for us. You can see these calculated temperatures here. They're not varying very much. I think it implies that we're going to need to use an analyzer in this process. What I did finally do is I said, okay, what if the temperature is 0.15 degrees or a bit more in terms of temperature up? How much methanol am I going to be in my overhead? And I'm way up. I'm a lot higher actually. So that might be either a situation where we go back and look at the specifications that we're going to sell the material at and say we're going to try and change the standard for selling DME with methanol in it so that we can actually control it with a temperature, or we're looking at having to buy an analyzer, pretty expensive analyzer. We probably need an analyzer anyway, but to put an online analyzer, that's going to be tricky. So I did. So I think we got a little bit of a question ahead of us on that one. We think I'll put an analyzer in anyway, but okay. Then the other thing I did is I looked at the reboiler as well, and essentially did the same sort of thing here, where I increased the temperature by a small amount from the base case, so by the 0.15, and I found that the composition wasn't changing very much. And not only that, but we're sending that material back as a recycle. So my thought here is that the bottom of the column is very easily controllable with temperature. So the temperature will be a good proxy for composition. Anyway, so that's what I was, that's some of the stuff I was working on yesterday. That helped me at least get my head wrapped around what kind of a control scheme we're going to need to use in this design. Any questions about that, you guys? Wow, everybody's here. Holy. Except for Seb. Yeah, Seb would have questions. Any questions about that? So now I guess we're probably in pretty good shape to design the tower. Liam, you got some equipment details that we can use, right? Can you just give me a sense of, I'm just going to draw like a little sketch here. You got a tower, right? How many sections of packed bed did you have in the tower? Say above the feed. Yeah. Just one? Okay, and one below? Okay, so all right, so I don't need to worry too much about it. I'll just draw it right off. So the first step in this game, you guys, is to start drawing yourself some little rough sketches. That's my rough sketch right there.
Oh yeah, completely rough. Well, it is rough for him.
So it's pretty rough. Actually, the real first step in this is to sit down with the process flow diagram and start putting the controls into the process flow diagram. But then when you want to draw the P&IDs, you start with some sketches here, because very quickly I start to box myself in and I go, oh, I'm running out of room, and I'm running the line all the way around and stuff like that. You do that on a couple of 8.5 by 11 sheets, and you'll get to the big sheets, and it'll look pretty nice by the time you're done, because you got it planned out a little bit better. So first thing to do is to get the tower itself drawn on the P&ID. And I know basically all my equipment is on the right-hand side of this P&ID, the condenser, the reflux drum, and the pumps, and all that good stuff. And then I'm just going to have the controls for the reboiler down in here. So I'm going to basically put the column right in here. I'm going to come over to the condenser here. It's going to have to be fairly high because I want to get the pumps down in here. And I need the reflux drum in here, and there's tons of controls around the top of the column, as well lots of controls around the bottom of the column, so I want to spread stuff out a little bit. And I want lines to be able to flow off the P&ID fairly easily. Okay, so let's take it one step at a time here. Like this. Too much coffee or something like that. I got a little bit of a shaky hand. Let's see if we can do it a little cleaner than that. Yeah, really. Maybe I'm getting old or something. A little bit better? Not much. Okay. So you don't have to draw this as I go, because I'm going to be making corrections. So let's see. Basically, I'm coming in on stage 12 of 17. So I'm kind of down towards the bottom here. I'm going to draw my inlet here. And I know there's going to be a liquid distributor. Underneath the bed here. And I'm going to come back and think about monitoring like temperatures and things like that a little bit later. Ideally, what I'd like to do is I would very much like to have some sort of feed control on the tower. But I'm going to come back and do the controls later. But I know I need some sort of flow control here. So let's put the tower packing in here. I bet I'm going to run out of space here on this one. Okay. I'm going to do that. So I'm just going to show the packing like that. And, whoops. Need a liquid distributor here. You know what, I should really go to the glitch manual and just get a better diagram of what a liquid distributor looks like. Here's my reflux coming in here. My vapor is going to come out here. I'm going to have lots of nozzles for relief valves and pressure transmitters and all that good stuff. That'll come in later. We're going to need a reboiler, and we're going to need some liquid levels in here. So let's put a high liquid level in here. Normal liquid level here, and a low liquid level right about there. What kind of a condenser did you guys design, Liam?
Not sure.
Not sure?
Yeah, we have a total condenser.
It's a total condenser. Okay. Any thoughts on the TEMA type?
I'm pretty sure we use
YouTubes? Okay.
like a double pipe. Yeah, double pipe.
A double pipe.
Yeah.
Okay. Probably it's in sections maybe. Okay. Like that. Like that. Okay, there's a little double pipe heat exchanger for us. I'll just draw the line in the middle just to kind of show that. Okay, so it's a very small heat exchanger. And then we got a reflux drum. Make sure when you're drawing vessels that are pressure vessels, they should have rounded heads on them. Like that. We're going to have a low liquid level, a normal liquid level, and a high liquid level. Okay, then we're going to come out of the bottom of that. And we need some pumps. So I'm going to put the pumps, I have to decide whether I'm going to put the pumps vertically or horizontally here. I did them vertically on my sketch, but I was starting to run out of space a little bit on them. So maybe what we'll do is we'll try and do this vertically, or horizontally, pardon me. Okay. There's one pump. And it's always a little bit of a trick whether it makes more sense to do them horizontally or not. There's the other pump. What you want to do for the pumps is you want to go to the wiki and grab kind of the cookbook of what a pump design should look like on the P&ID. Let me just fire that up right now. That's what your, that's kind of the standard layout for a pump. And they're all duplicates. So what you can do is draw that out once, stick it on a Post-it note or photocopy it or something like that, and then you can move it around almost like you're using CAD. First of all, you want to draw a motor. And so the motor is the M that hangs off the bottom there. And then the motor needs a power supply. So the power supply for the motor comes from what they call the motor control center, the MCC. And the symbol for that is an eye in a diamond, which is confusing to, can be confused with an interlock. Okay. Then you need some way to turn the pump on and off. So you want to put a hand switch in the field, and you want to be able to start and stop it from the control system. So let's do that. We'll put a hand switch in the field, which is just an HS with a circle around it, and a hand switch in the control system, the DCS. Okay, so we've got that. There's our electric stuff, yep. What's the eye? So the eye right there is the motor control center. And the reason why it's the same symbol as an interlock is because there's a lot of relays in a motor control center. Mike?
So are those two pumps like, just one of them is backup? Or
Yeah, you've got two pumps, one's redundant to the other one. Yep. 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 No, usually they'll just have one running in the process industries. Yeah, if you're in an HVAC system, they often have both running. Okay, so we need some piping for it as well. And the first thing you'll see there as you come in from the left-hand side is an isolation valve. So we need an isolation valve in order to get the pump. We may put it in the vertical section, actually. Let's do it on the vertical piece here. Like that. And if you guys don't know what a motor control center is, I'll take you for a little tour through the Integrated Learning Center. I'll show you a couple of MCCs. So yeah, we can go up to the fan room and look at the MCC. Oh, we do have, Seb is here. Hello, Seb. Okay, guys, quiet so we can hear the question.
I have a question about the hand switches, because a lot of pumps can run either automatically or manually, so they have a switch for both.
Yep.
Is that something that we would have to indicate on the P&ID, or how would we do that?
Yeah, a good way to do that. Usually what you do is you have a standard. Every electric motor, every pump has the same standard for the way the stop-start stations are going to work. And a lot of them have basically a rotating lever, I guess, like that. And there is an off position in the middle, an auto position, and an on. And so and then on top of that, right, you'll have a push button that's the on and a push button that's the off. So that's kind of a standard field-mounted control. So it's kind of shown like this, only there's the toggle that's missing for the auto on-off.
Okay, so if we were to draw that on P&ID,
Yep.
how would that go?
So you can either put on, auto, off on the P&ID, or you can just assume that it's there because you do it for every single pump. So how about if we put it on, and then it makes it more clear? Sound fair?
Okay. But will we have to do that for every single one?
We're gonna have to do it for all of them.
Or is there any pumps that are there any pumps that we would just be running manually or whatever, like a sump pump, for example?
Yeah, maybe. Yep.
Should we be considering which buildings might have ratings?
We probably aren't going to get to the level of designing the building sumps and stuff like that, but Yeah, you could definitely do that. Guys, shh. No, we're not gonna worry about the utilities because they're gonna be built into the utility prices for now. Okay? Because we're not gonna do the utility P&IDs in 470.
So for like the condenser and the heat exchangers that do use utilities, like we don't
We're not gonna worry about the pumps for them.
just have like the streams of cold water.
We're just gonna have the streams come in, yeah. Yep. Let me get there, Seb. You're getting ahead of me. Good questions, though. Any other questions, though? Okay. So we've got our pump isolation valves here. The next thing we need is let's just draw the piping. Usually there's a reducer right on the inlet to the pump. So just because the pumps are almost always one size smaller than your line sizes. And I'm just going to work backwards here. We need a strainer. So this is a Y strainer. And usually there's a small valve on there that you can drain stuff out with as well. The Y strainer just kind of keeps the lunch boxes and the screwdrivers out of the pump. Small solids just go right through the Y strainers. They're really just there to protect the pump. And so if I put a drain on the Y strainer, I may not need one in the actual piping. And of course, I need to move that around so it can look a little bit better. If you can get your, if you can line stuff up on a P&ID, you guys. So you'll see I tried to line those two valves up. If you can line your instrumentation up, if you can line your valves up a little bit, then it all looks a little bit better. Oh, we're missing a pressure indicator. There it is. Okay. So we need a pressure gauge. Like that. It's going to need so a pressure gauge is a PI, and it needs a little isolation valve. Like that. And maybe if we walk up through the aisle, you'll be able to see all this instrumentation on the pumps as well. So that's the pump section. Now we just need to kind of connect it up to the reflux tank. It's questionable as to whether we want to put an isolation valve right on the reflux tank. I think stuff will be pretty close in our process, so we maybe don't necessarily need it. But a lot of the time, you would put an isolation valve right around the, right on the tank. So just for the sake of good design, I'll just do it. I don't know whether we'd really need it in our design or not, but we'll do it anyway. Okay, so, and then the other, oh, I screwed up. I'm going to switch I switched the direction of my pumps around here. There we go, that'll make life easier for me. So some people draw pumps vertically like this because the discharge on most pumps actually is off the top. And some people hate that because that's really the standard for drawing a fan. So there's I'm going to use this as the discharge on my pump. And I need a reducer installed backwards. I'm going to put the PI in first so that I'm measuring the differential pressure on the pump right as it comes out. And the reason you want to measure the pressure on the inlet and the outlet of the pump is that when you calculate the differential pressure, you can go to the pump curves and find out what the flow through the pump is. That. Like that. Then I need a check valve. Check valves allows you to start the pump up and prevents flow from going backwards through the pump when if it's online and but not running. And we need okay, so horizontal lines break vertical lines. So there I am. Here's my isolation valve there. And I'm out of my pumps like that. And now that I think about it, I'd actually prefer to put the inlet PI downstream of the strainer. So I'm going to do that right now. Just because if the strainer starts to plug a little bit, we can check. We'll get a more accurate reading of the inlet pressure. There. Ah. Let's do this. Like that. That's better. Okay. And then we've got to get back up into the reflex line. I want to leave myself lots of space here. So I'm going to put it right in the middle of the P&ID like this. I may end up having to move it. We'll see. Okay, so there's our basic piping for the overhead line. We're going to have some cooling water supply. Let's go right off here. Cooling water supply, cooling water return. It did occur to me this morning that, and you guys probably thought about this too, we might be able to use an air cooler on these towers, which would be kind of an interesting design because we're trying to make this very small scale and very modular. An air cooler would actually be kind of a nice, it would use some electricity because you need a fan turning on, but it would reduce some of the piping and some of the complexity of the overall design possibly. So if I had to go back and redesign this process, I'd be seriously looking at maybe using air coolers because we're certainly at temperatures that could make that work. We could actually put the air coolers kind of on top of the container and have a fan that kind of blows up through them. Okay, one thing is that we're going to end up having a control valve in this line. And if that's the case, then we need a minimum flow bypass. So we're going to put a restriction orifice. And we're going to come back into the tower, or into the reflux pump. There's my minimum flow bypass. And I'm purposely not going to put a valve on that so that people can't accidentally close that valve and block off the minimum flow bypass. So I might even put a note on that because it's easy for there to be miscommunications. So note 1, no valve in line for minimum flow bypass. Yeah. What's a check valve? So a check valve prevents the fluid from going backwards, right? And if you want to start one of these pumps up while the other one's running, what you would do is, let's say this one was running and this one was off. You first need to open this valve and open this valve so the pump is actually online, okay? And you might actually, and then what would happen if you didn't have a check valve is this is the higher pressure. And so this pump would suddenly start pumping back through this. And it would just basically be short circuiting. So that check valve prevents that. Now there are some situations where the pumps are operated at fairly high temperatures. And you want to slowly heat that pump up somehow. So a way to slowly heat a pump up is to put a little tiny jumper across the check valve with a valve on it. And then you allow a small amount of the flow from this pump to stream backwards through that pump and just keep it hot. So if you want a hot spare pump, then you need to put a small bypass around the check valve. No, that valve there is the actual isolation valve. So that if you close that valve, which is this valve here, if you close this valve and you close this valve, now you can take the pump out and do maintenance on it while the system's actually operating. Liam?
What's the valve after the pressure indicator before the strainer?
So I've shown that on the actual strainer here, but what it is just it's a small drain valve. So like a 3/4 inch drain valve. And you can put that on, or sometimes people will just do it on the strainer itself. So, and sometimes they'll even put a vent valve in as well. So they'll put a little 3/4 inch like this, so that when you open the drain valve and you want to get everything out, there's somewhere for air to kind of bleed into the system. So you don't see that on every pump, but sometimes they'll do that. And even sometimes they won't put the drain valves in, and what they'll expect the operators to do, or the maintenance people, is to crack a flange. That's not really very good practice. Yeah, you're better to have a valve that you can open and depressurize the system first.
But you can also just put that drain valve on the strainer.
Yeah, you can put the drain valve on the strainer. Yeah, yeah. So it kind of becomes a sort of a standard for how the company wants to do it. Ted?
What if you wanted to add a PSV or a crack stroke to the line?
If
Pressure switch to the line, sorry.
depends on where you want to put the pressure switch, but you probably
You want to have it on the discharge.
probably put it on the discharge, and you probably want to put it inside the block valve as well. So these are the block valves. Okay, so they're on-off valves. They're usually a gate valve. They're usually a gate valve like that.
And a PSV. I know you put the PSV on the discharge end, but for the pump side, where would we tie it back into the pump line? Would it be after the strainer, before the strainer?
Relief valves are a trick there for sure. If you needed to put a relief valve, the only reason you need to put a relief valve in is if you got a positive displacement pump, or you have a fluid that is going to thermally expand due to ambient temperatures. So if you have a fluid that has a high thermal coefficient of expansion, some of the fuel oils have that situation. Most of the chemical plants like methanol and stuff like that, they don't really bother too much about it. But if you did need to put a relief valve in, Seb, what you do is you would put it here, like that, and you either vent it back to either vent it to atmosphere, or vent it back into a tank like that, a reflux tank, where somewhere to go. That's how I would do a relief valve if I had to do one on this system. I don't think we need one. It doesn't really matter where it is. So.
Well, it would be on the discharge side that it's at high pressure, right?
Okay, yeah, okay, you're right. It depends on what the situation is that you're trying to protect. I was thinking thermal expansion. If it's thermal expansion, then it doesn't matter whether it's on the inlet or the outlet. If you're trying to protect against like a positive displacement pump actually overpressuring the system, then yeah, it needs to be on the discharge, for sure.
Well, for
Yep.
protecting the system for overpressuring, is that just for positive displacement pump, or could that be for any pump?
It could be for any pump, but the better design for, if it's a centrifugal pump, then it has a flow versus delta P curve that's very predictable. And as long as the inlet pressure doesn't rise too much, then the discharge pressure doesn't rise any more than what it says on the curve. And so you should really be thinking more along the lines of designing the piping system to withstand the maximum discharge pressure of the pump rather than putting relief valves in. If you start putting relief valves everywhere, you're going to have a nightmare on your hands. Yeah. So that would be something you would do if the piping system was all installed, and then somebody came along and said, oh yeah, but what happens if such and such happens? We start to overpressure the piping, and you don't want to rip the piping out and put new piping in. But if you're designing this from the ground up, there should be no reason why you don't just design the piping system for the design pressure of a pump that's shut in. So I'm going to assume that we can design this without the relief valves for that particular case. We are going to get into some relief valves. Any other questions?
Why the minimum flow bypass?
Why the minimum flow bypass? Because we're going to have a reflux. we're going to have a valve in here that controls our reflux. Okay, that's going to be a control valve like that, and it's probably going to be a fail-close valve. And we don't want to shut the valve in, we don't want to shut the pumps in so they have zero flow. We always want to have a little bit of flow going through the pump.
Sorry, the bypass, would that be the restriction, or would that just be like a choke? Or?
It's just an orifice plate.
Oh, okay, so we'd be continuously running stuff back.
Yep. Yep, this will be about 15% of the flow of the pump. When we get to the pump sizing, I'll explain that in more detail. Okay. What are we doing for time? We kind of have the top of the tower basically piped. Let's just get the bottom of the tower piped. We need a reboiler. What kind of a reboiler did you guys use, Lim?
Double pipe as well.
Double pipe? Okay. I'm going to change to a stab-in bayonet, just for almost more for fun than anything else. Okay, just because I want to illustrate a couple little things here. So I'm just going to give myself a little bit of space here to draw it. I just want to illustrate a couple of principles that I'm not saying that a stab-in bayonet is better or worse. Okay, but I just want to show. Okay, that's a kind of a lousy job of drawing a stab-in bayonet, but there's my normal liquid level. And I'm going to bring my low liquid level up a little bit, and my normal liquid level is going to be here, and my high liquid level will stay there. Okay, so basically what it is, it's a type of shell and tube with no shell. The vessel itself is the shell. And I'm going to need some steam coming into it. So here's the steam. And I'm going to send that material back as condensate. Whoa. A little bit wonky. Condensate return. I know for sure. Let's put some isolation valves on the heat exchanger because it's just good practice, like that. And in order to get the steam into the, to control the steam going in, I know for sure I'm going to need a control valve. And I'm actually going to want to measure the steam flow as well. Let's just put the control valve in for now. But I'm going to add the flow control in a second here. I'm going to want that to fail closed. And in order for me not to blow steam through the heat exchanger and down into the condensate return system all day long, I need something to stop the steam from blowing through there, but allow the water that condenses in the heat exchanger to go through. What do I need? I'm looking at Liz. You are right. We need a steam trap. If you don't know what a steam trap is, there's a bunch around the ILC, a lot of them. And the easy way to think of a steam trap is a box that's got a ping pong ball in it. There are all sorts of different types, but this is just an easy way to think about it. Okay, so let's say you have a little ping pong ball like this. Here's our, coming from the heat exchanger, and it's got water and steam that's coming down through here. If there's no water in the trap, then the ping pong ball sits down and it just seals, and so steam can't blow through. As soon as some water comes in, the water floats up, or the ball floats up, and the water can go out through the steam trap. Really, really simple. Okay? There's lots of different ways to do that, but that's the principle that you're trying to do. Some steam traps also vent air as well. If you get a little bit of air in your steam system, you want to get rid of the air. You want to pass the air through the system. And typically, because steam traps are fraught with a lot of failures, they'll put a bypass around the steam trap. Maybe like this, so that you can operate the piece of equipment. Okay, so I've got 2 isolation valves around the steam trap and a bypass. That's just like a standard thing. People just always build steam trap stations like that. Okay. We need to get our column feed in here. And whenever you've got a connecting line from one P&ID to the other one, you should indicate the drawing number. Now we're doing drawings just with sheet numbers, but a lot of the time people do it with, so I don't know, what's the sheet that's upstream of this? This is sheet 6 or something like that? Who's got the P&ID map? Excellent. Okay, this is sheet 6, so we're coming from sheet 5. Like that. Ideally, we would like to actually have flow control on that feed system. So here's where, if I put the flow control on this P&ID here, okay, you can't actually tell whether that control valve is close to this piece of equipment or further back and should be on the other P&ID. So this is where if you start splitting P&IDs up okay, so I kind of think of this as being the control feeding the tower, but actually that control might be doing double duty. It might be doing something on the upstream P&ID. So whether we put the control valve here and bring some signals in, maybe that's what we'll do. So this is, let's call this a flow valve. I don't know whether it actually is or not. And this might be coming from a level control, it might be coming from a temperature control, it might be coming from a whole bunch of different things. So, but this is from sheet 5 as well. I'm just gonna make the assumption that it's the LIC, but I have no idea what it is. So if I'm not sure, what I can do is just put a hold on it, like that. And that just tells somebody, whoa, hang on, that's not the final design. We need to go back and check that at some point in time. Okay, that's that. Now we need the bottom of the tower, product off the bottom of the tower. And I somehow have to get that off there. So I got to go right through my instrumentation. I think I've got enough space here that I can probably whiz my way through and around there. So let's give that a whirl. Yep. There we go. Is it pretty level? We're for sure going to need a control valve in here. Most control valves have reducers around them. So I'm going to show the reducer like that. I should have showed the reducers on these as well. Like that. Probably going to need a reducer around this set of reducers. Okay, not compressors, pipe reducers. And what did I miss? There's something I missed. What's that? But I'm missing a major pipe. I'm missing a major pipe. I'm missing a very important piece of piping on here. The product line. Exactly. Okay, so horizontal lines, break vertical lines. We're going to need a control valve on there. Probably going to fail it closed. I get all my failure positions. Boom, boom, boom. I failed that one closed too. And we probably are going to need some control on the cooling water as well. Like this. There's a bunch of different ways to do this. Whoa, that's a terrible valve. Ugh. There we go. Like that. Okay, so now we have our control valves on there. We've got the liquid levels shown on here.
Dave?
Yep.
Just as a question, for the control valve and cooling water supply, would you want it to be failed closed or failed open?
Oh,
'Cause,
yeah, we might fail it open.
yeah.
Yeah, that's true. Yeah, I did talk about that in class. You're probably right. We might actually fail that open. Yeah, there we go. I think you're right, Liam. We probably would fail that open. We can go back and think about it from this when we start looking at the safety on it as well. I think we're good for the piping. Now we're missing a whole bunch of instrumentation here. Maybe we'll start with what we maybe think is the easy part of this, which is the bottom of the tower. So we've got the material coming in here, plus the reflux flowing down in here, affecting the liquid level. We need to measure the temperature. We kind of talked ourselves into the fact that we can probably use temperature in the bottom of the tower to control composition, or level. Sorry, to control composition. So let's get this in here. So in order to do that, we need to put a temperature element in. And that temperature element needs to feed into a TIC. If you want to actually make that a temperature that you can read out in the field, then we need to make it a temperature indicating transmitter. For now, I'm not going to worry too much about it. I probably do want to have a temperature alarm high and a low alarm, so I'll just put that on the P&ID like that. And in theory, we've got this choice of manipulating level with the steam. If we drive the steam harder, that'll basically boil more material out and it'll drop the level. So we need to measure the level as well. Okay, so if we drive that harder, it's going to boil more material out, it's going to drop the level. But the game here, it's not that simple sometimes. It's like when you're boiling potatoes on the stove. Sometimes what happens is you start to boil it a little bit harder, and what happens is you start to create bubbles in the material, and it actually causes the liquid level to rise. So it can fool the level transmitters. in the long-term response is boiling this harder will drop the liquid level, but the short-term response might be to actually what they call an inverse response. It might actually cause our measurement of level to look like it's going the wrong way, which will open the steam control valve more and more and more and more. So it's kind of working backwards. So you can build a control system that kind of avoids that. We can also probably flip it around and put the level control on here and attach the temperature control to this valve. So that would probably help us with the inverse response in this tower. What we should do is we should go and look at the simulation and look at the flow rate coming off here versus the boil up that's going off there. And let's have a look at that. Let me just squeeze by you guys. Let's see which ratio dominates. Let's see if TE. Okay, so let's look at the column profiles here. And okay, so the liquid that's coming down is, so the liquid coming down into that pool is 720 kilograms an hour. And the vapor that we're driving out of there is 465. And therefore, the liquid that we're taking off the bottom of the tower, if I could make this bigger. Oh, there it is. Okay, is 254. So one of those is not 10 times the other, which means that we can hook the controls up either way. It doesn't matter which way we hook it up. If this flow were to be 10 times the boil up vapor rate, then we would probably want to put the level control on this. If the boil up rate was 10 times this, then it would drive us towards putting the level control on the steam value. But we're somewhere in between, so we can start to look at other criteria here. I'm inclined to try and get rid of the inverse response by measuring temperature here. So I think I'm going to put the temperature control onto the steam flow, onto the steam here. So now we could make this simple and just tie the temperature right into the valve here. But a better way to do this is to do a measurement of flow. So I'm going to put a flow indicating transmitter here and a flow indicating controller. Here. So, and then I'm going to tie the temperature indicating controller into, I'm going to cascade it. So the temperature indicating controller is going to send the set point to the flow controller. The temperature indicating controller is going to tell the flow controller, I need 100 pounds an hour of steam, or whatever the number is. Okay? And the temperature indicating controller is going to be measuring basically the composition in there. The only thing that we could consider here is if there's likely to be much variation in the pressure in the bottom of the tower. I don't think there will be, but one added level of complexity that we could do here is we could put a pressure transmitter on at the bottom of the tower. And we could send that pressure transmitter down into the composition control. And now we're measuring the temperature and we're measuring the pressure, and we can create a bubble point curve in the software. So we can actually then control composition. So if we're going to do that, we're going to call this a composition controller. That's an XIC. Actually, you know what? We're probably interested in both in the temperature and the pressure. So let's put a TI, so just an indicator in the DCS like this, and a PI as well, like that. So we now have temperature and pressure, and then we're going to put a composition indicating controller in, like that. And we're going to send the software values of pressure and temperature into the composition controller. And then that's going to send a signal to the flow control. And judging from just like a little bit of experimenting on the in the simulation, I think that's probably a pretty reasonable way to do that composition control. We're not really too worried about what the composition is down here. It could be a fairly loose control. Okay, now we got to get the level control in there. And the level control is made complicated by the fact that that swell is going to affect the level transmitter. If we could eliminate that a little bit, that would be a nice thing to do. So one way to do that is to take some nozzles off the side of the tank and build, you can do it either internally or do it externally. Build like a little stilling well, like this. What this looks like is, it looks a lot like one of the big coffee urns. You know, the big coffee urns have like a little sight glass on the side. And if you notice when you actually start draining coffee out of the pot comes down like this, and the sight glass actually doesn't drop as fast. So it kind of dampens the actual measurement of level out of there. So it's going to be less or more slowly affected by the swell in the from the reboiler. There's our level transmitter. So our low liquid level is there, normal liquid level, high liquid level. And I've got the liquid levels kind of above the tubes in the reboiler, so I'm trying to line them up with the tubes in the reboiler. And then we need a level indicating controller, like that. And level is one of those things that we could let float around a little bit. So it'll be a slow variable, and if it is a slow variable, then we need to cascade it into flow again. So we're going to do that as well. So I'm going to put a flow indicating transmitter here. I'm going to put a flow indicating controller here. Okay, that's a terrible. There we go, down low. I have trouble rating. Try that again. Okay. Clear as mud. Level alarm high low on that. Any questions there? Probably we should put isolation valves on the column like that. If you ever want to be able to pull the control valve out and keep and not have to decontaminate the system, then some people will put manual valves around the control system. You can close the valve, crack a flange, pull the control valve out, and do repair on it. Our process, again, is kind of small, so we might not really need that kind of stuff, but I'll just kind of show it there for example. So if you look at some of the safety incidents that have happened in the past, some of them have been because level transmitters have failed or read wrong. and so forth. And it's not a bad idea to have some sort of redundancy in this game. So putting some level switches in is not a bad idea, probably. Also, a sight glass wouldn't be a bad idea as well. So we have this stilling pot, and let's put a sight glass across it here. This is why I need a lot more space. I should have given myself a lot more space here. There's a sight glass there. Let's put a level switch high in. Like that. And a level alarm high. Like that. And let's put a low level switch in as well. You can see how these things get complicated fast, eh? And I've purposely put the level switches inside the level transmitter so that if the level switch is alarming, I still should be able to see something in the level transmitter. That was one of the, that's one of the kind of the learnings from one of the safety incidents that if you look at the CSB, you will see. Maybe what I should do is get rid of this pressure transmitter, just wind it around here. That might be a better way to like that. That'll clean this up a little bit. That look a little bit better? That's about as clean as you're going to get it. And I have provided valves on the level switches, which means that they could be bypassed. So we might be car sealing those open. That's not too bad. See if I missed anything from my little sketch. Pretty close. Any questions about the bottom of the tower? Okay, let's do the top of the tower then. Now we really do need the pressure and the temperature on the top of the tower. And we're going to need to put relief valves in. So let's put the pressure transmitter in first. Like that. We need to measure the temperature. The best way to measure the temperature is to have the flow of the fluid basically impinging on the temperature element. So the best way to do that is put the temperature element right in the elbow of the piping. So it's actually, if you looked at that piping, here's the piping like that. We're actually going to put the temperature element. There's the thermal well. And the TE is going to stick right into that, so we got really high velocity going past that, that temperature element. That's going to give you the fastest response. That all clear as mud? Now, we've got the temperature, we've got the pressure. We're going to have some composition here. We might actually need an analyzer. So let's put an analyzer in. So analyzer, and this is easy for us because we don't really have to worry about what kind of analyzer it is. We just write it down and somebody else figures out what it is. We want to actually measure methanol and water. in the DME. And then we're going to need an analyzing and indicating controller. Like that. That analyzer is going to be really slow. So whether we're controlling this with the composition or this with the composition, it's probably going to be some sort of a cascade loop, because that's going to be slow. And if we use temperature, that's going to be a lot faster. It's just that it's going to be tricky to get much accuracy or much. We're not really going to infer the composition very well. We'll know if it's a long way out. So we definitely need to cascade this. And we're going to put the flow controller in here. One thing you'll probably see me try and do, I kind of do it a little bit subconsciously, is where I can do it, I'm trying to draw my controls from left to right and top to bottom. You're definitely going to see me break this rule quite a bit, but I find if you do make the controls kind of go left to right and top to bottom, so you'll see I'm going from left to right here, LIT into the LIC. The LIC is then going down into the flow indicating controller. The FIT is coming from the left and into the FIC like this. It's partly because the flow indicating transmitter is always going to be upstream of the valve, so that just naturally happens that way. But it makes it a little bit more readable, I find. In this case, I need to put the flow transmitter upstream of the valve. And so I've had to go kind of backwards in this. And I probably, to make this more readable, I probably could have put the flow controller over here, flip the valve over this way. Should I try it? Let's try it. Let's do it. There we go. Okay, so let's use a composition indicating controller here. And it's going to send a software signal as a set point into the flow controller, and it's going to get its signal from the composition controller here, the analyzer controller. And if we're actually going to try and use bubble point here, then we definitely need pressure, compensated temperature. And we probably want to bring this temperature down, whoops, dash line. Like that. Okay, there's my composition control on the tower. Now, what I should have done is I should have gone and checked to see whether this flow was 10 times this flow or not. I think I did that last night, and I happen to know that I can flip these around either way. Yep.
Just as a quick question.
Yep.
If you've got the C in line, is the only reason that you're having the PI and the TI feed into the XIC just because of speed?
Yeah. Yeah. Yeah, it's definitely speed. It's speed and reliability, because the analyzer control is probably not going to be online all the time. You're going to have to do repairs on it and stuff like that. So you need something to back it up that actually is going to be there for you when you need it. I did a crappy job at drawing that PI, so let's draw that a little bit more, a little less. Am I wearing you guys out? Okay. That's a little bit better. And I might even, me personally, I would have put pressure control on this column, And the way I would have done it would be to go over to the cooling water system and maybe do that. So I might actually turn this into a pressure controller, in which case I can go all the way over here. I can put I can cascade it into a flow control on the cooling water. So this is one way to do it, and not necessarily the recommended way, according to what I've been reading today or yesterday. It might be all right on this small system. Okay. Whoops, that should be a software signal. One controller to another controller has got to be a software signal. Okay, if you see a signal between two controllers, they should always be software, or 99.9% of the time they will be. So that gives us pressure control on the column by manipulating the cooling water flow rate. There are a bunch of different ways that we could do this. We could actually do pressure control by just letting the cooling water rip. So you take all the controls off the cooling water system and just let it flow at maximum velocity. And then what you can do a couple of different things. You can put a control valve in here that is measuring the pressure back in here. And if the pressure gets a little bit too high, the control valve opens and closes. So I think we did a tower like that a long time ago, and it worked really well. The recommendation, that's a little bit of an old recommendation, but still probably quite relevant, is to let the pressure, keep it between bounds, but not try and hold a really accurate pressure 100% of the time, like not hold it at a particular valve. So kind of have loose pressure control. I'm not sure whether that's the right way to do it with this particular tower, because we're trying to get down to such low concentrations of methanol in water. If we let the pressure float around very much, I'm not sure how good that's going to be for our temperature control, composition control.
I was just wondering if you don't have another control valve, then you're not going to be able to control the temperature.
If we don't have a control valve here,
Well, yeah. Like
you mean?
So like I think right now you've got pressure, composition, and I'm assuming you're going to put in a level control.
Yeah.
That takes all of your control valves that you have currently drawn in.
Yeah.
Which means that you're no longer controlling temperature directly. So it might be better to put the pressure, like do the pressure system as you said, put a control valve on the feed into the condenser, and then keep that control valve on the cooling water supply there, but have that tied into the temperature.
I have to think about that one a little harder, Liam, because we're really controlling temperature with this composition control. Really, we're controlling temperature.
But then you're not controlling temperature directly. You're just controlling it through the composition. And is that what we want?
Yeah, well, ultimately what you're looking for is good composition control, right? Ultimately what you're really looking for is to meet the required specs for sending DME off. So that's probably that is the most important control loop in this whole P&ID, bar none.
Yeah.
Right, everything else is a slave to it.
Still let the temperature float. Because you're not controlling temperature directly.
Yes, you're not controlling temperature directly, but I think temperature is a very good proxy for what the composition is. Apart from the fact that the curve is really flat, right? The composition doesn't, or the temperature is not changing very much with the kind of compositions that we're trying to achieve down here. The reason why people are saying don't have a lot of flow control on the heat exchanger, I'll cover it a little bit more in detail on Monday afternoon. But essentially what happens, if you start to throttle this control valve, then the result is heat exchangers all work with LMTDs. So here's the length of the heat exchanger, or the Q valve, the heat flow across the heat exchanger. Here's the temperature here. Here's our hot stream here, like that. And our cold stream comes in at some low temperature here, and we probably have a design kind of like that. If we start to reduce the duty on the heat exchanger and start restricting the flow rate, in order to reduce the duty, that temperature is fairly fixed. So Q is equal to UA LMTD. The U and the A are almost fixed. Well, the A is fixed, and the U varies a little bit with the flow rate. But what ends happening is you end up doing this with the cooling water. And so that brings the outlet temperature of the cooling water up. And since we have stainless steel, if you start to get above 50 degrees Celsius, we have stress corrosion cracking occurring.
But we also have a limitation of no more than 45 degrees C.
Yeah, and we don't really want to return it back all that hot as well. But that's, yeah. So we've designed it for like 45 degrees Celsius, and if it starts to swing up, you'll hit the 50, 60 degrees Celsius potentially, and that's going to cause stress corrosion cracking. It's going to send the water back a little bit too hot. So one of the recommendations for this cooling water control system is really actually just pick up the temperature on the outlet of the cooling water and control the inlet flow rate so that you hold it at 50 degrees Celsius. Just let the cooling water rip. So that's one way to do it, but you lose the pressure control with that. So in order to do the pressure control, you need to either put a valve in here to kind of throttle, hold the pressure back in the tower, or let it come down. Another way to do it is to allow if it's a shell and tube, you can actually flood the condenser on the process side and reduce surface area. I'll maybe talk about that a little bit more on Monday. But so one thing we might want to do here is we might want to put a temperature element in here and maybe some sort of a temperature indicating controller like that, so that if the temperature on the outlet ever got higher than 50 degrees Celsius, we start to override the pressure control and start to drive the temperature, start to increase the flow rate into the flow controller. So now I have to kind of find out exactly what the best way to do an override control, how to show an override control. But one way to do it would be to do it with a hand switch like this. One possible way to show this. I'll check with my instrumentation friends. Do this like this and show it with a greater than sign function. So that's probably not the right way to do it, but I think it kind of gets the concept across, where the hand switch is basically selecting the greater of the two signals from the pressure controller or the temperature controller. If that's not the right way to do it, I'll go figure it out and fix it on the board. So that's something we could do. We probably want to put a temperature alarm high on there as well. And we should definitely need alarms on almost everything. So we definitely want a pressure alarm high on here. Okay, so we are missing still the level control on the tank. That one's pretty straightforward. There's not a lot. There's nothing like the inverse response that's happening on here. This one's just pretty straightforward. I'm going to give myself a little extra space so I can put some interlocks in. So let's show the level indicating transmitter here. Here's my level indicating controller here. Whoops, let's do flow control. Let's cascade a flow control in there as well. I know it gets like this. Just take a picture of it afterwards, you guys. I'm going to leave it on here anyway. Okay, so there's my level controller cascaded into the flow transmitter. We're going to make that fairly loose control. And what I'm really interested in doing is protecting the pumps from running dry. So not only do I not want the pumps to run deadheaded, so that could deadhead the pumps, but we also don't want the liquid level to get too low. So what we want to do is we want to shut the pumps off if the level gets really low. We're going to do that with an interlock. So what we're going to do is we're going to show a level switch low. Do a low low because we have a low already on the transmitter. Like that. We'll put an alarm in at the same time in the control system so that we know about it. Like that. And then we'll just tie it right into the motor control center on the pumps. And we actually have 2 pumps, so we've got to tie it into both motor control centers. Like that. So that'll stop us from accidentally damaging the pumps. We're probably not too worried about high level. If we are, we could put an alarm on it. We put a level switch and a high alarm in if we want. I'm not sure what we would really do with it. Like that. There's the basic process control system with some of the interlocks in it. So we've thought about some of the safety systems. The other thing that we might want to do is it's possible to overpressure a column just by basically boiling the vapor by basically the reboiler creating so much vapor that it starts to overpressure the system. So we might actually want to have an interlock off the pressure control system that shuts the steam valve off. In order for me to do that, I've got a whole bunch of writing in here that I got to write, so I'm going to move this up. So I'm going to redraw that. Sorry about that. There we go. Now I got some space in there that I can work with. So this is probably going to be a cascade loop as well. Okay, so from the pressure controller, if I see, or maybe a pressure switch actually, let's do it with a pressure switch. Like that. I want to alarm it. Like that. And what I want to do is I could send a signal from the DCS from one controller to another controller, do it in software, or it's a fail-closed valve. I can just interrupt the electric signal. So I'm going to put an interlock in here, like that. And I'm just going to hardwire it into the valve. Okay, now wait a second, before you write that down. That's one way to do it, okay, but the problem is, if it's that valve that's stuck, okay, if it's that valve that's stuck, that's why we got too much steam coming in here, that's not fixing the problem. Just cutting the power off, the valve is still stuck. I need another valve. So I can put the valve on either side. Let's put the valve here. I'm going to make it an on-off valve, so it's going to have a square on it like this. Like that. And I'm going to do it like that instead. So I'm not going to bother with the steam control valve. I'm going to assume the steam control valve is knackered. And I'm just going to shut an isolation valve on the inlet to the steam system based on that high pressure switch. So now this is all hardwired through here. The control system could be not working, and this system would still all work properly. One thing that's not a bad idea is to put over here your interlocks. Give them a name. So DME column high pressure. And maybe just describe DME column high pressure shutdown of steam. So I'm going to write DCHP. And then if we want to, we could actually tie this into other controls. I don't know whether there's anything we would do here, but like drive the cooling water open or something like that. Let's make this just a little bit cleaner line. There. So there's an interlock on high pressure to stop the column from overpressuring. And if that doesn't work, or there's another failure, then we need a relief valve. And I'm going to blow that. I'm going to blow the relief to atmosphere because I think it's a pretty tall tower, and it's small. And I'm just going to deal with the environmental issues of that. Because I'm putting enough controls in that, I'm going to make sure that relief valve never blows. And so I've got one interlock there, another interlock there. Did I think of any others? Oh yeah, there's one other thing that is kind of handy to know, and that is the differential pressure across the various beds. So we might actually be interested in putting a pressure differential indicating transmitter. This is just for information, like that. But if we do have high pressure differential across the beds, it may be an indication that the control valve has gone, there's something wrong with the steam. And so you might actually provide some sort of an override on that. And I'm going to put another one in here. Pressure differential indicating transmitter. Like this. So I had the bottom of the tower as well. Let's put an alarm in, pressure differential alarm. High. You can see why I spread stuff out, eh? Now what's left is to put some monitoring things in, just pressure gauges, temperature gauges, anything else that we might be interested in. So I'd be probably very interested in knowing what the reflux drum pressure is, so I'd probably put a pressure gauge on there. I'd also be very interested in knowing what the temperature is, so I would put a TI in there. It's just a thermometer. I'm probably very interested in knowing what the cooling water pressure and temperature is. So I'd probably just do a dual gauge, PI-TI gauge. These are available. Sometimes you'll split it up into two different gauges. Sometimes you'll do it just as one. Probably a valve on there. Actually, I'm not sure whether they do put a valve on there or not. I'm not sure whether they can do a valve on that. It's not cooling water, so I'm not going to worry too much about it. Yeah, I have to check to see how they make those gauges or not, whether you can do that. So if the two bubbles are touching, then that means that they're one device. So I know what the temperature of the reflux is from that. I know what my pressure is. I've got my pressures here. DME storage. Oh, we probably want to know how much DME we're making, right? So let's put a flow totalizer in. So that's going to be a FQI. Flow totalizing indicator. That'll be handy. Yeah.
What's the Q?
Totalizer.
Totalizer?
Yep. Yeah, so we'll know from there how many pounds of DME we're making over the course of a year or day or whatever. Yeah. If we were selling that like we probably are kind of at the pumps, then we might need much more accurate flow transmitter here. We might actually make that a mass flow meter just so we improve the accuracy. And okay, so relief systems. I've got a relief valve there that's protecting the column. There's no valves all the way through here. So that relief valve is protecting the reflux drum as well. I think I'm kind of done. I'm probably going to think of some other stuff this week. That always happens as we start talking about things. And so I'll mark up my either mistakes or things we want to add with a red marker so you guys can see what I've changed as the week goes on. Any other questions, though?
So for Wednesday, we obviously don't need this.
Right.
But like wherever you have PIC, TIC, or FIC, do you want those drawn in as well, like for the PFD? So like you have like would you say like coming off of the top of this column, PIC going into control valve on reflux, and or would you have like, or would you just show the XIC?
It's up to you guys how you want to do that. I would say if you've got a cascade, I guess the way I would have done it is I think I probably would have just had the XIC.
So just show the XIC.
Just the XIC. But if you want to show the cascade as well, there's nothing wrong with doing that. So it'll just make your P&IDs a little bit easier when you're doing your first little sketch. Yeah. Yeah. This to me, this is my first little sketch. This is kind of this is sketch Rev 1. This is sketch Rev 2. Then once I've got this all sorted out, then I would actually go and put it on the big paper. Yeah. Yeah, because obviously I cramped myself in here, so I made it kind of messy looking, but. This is good enough for me that I can put this onto a big piece of paper and not worry about it. Or if you want to use Visio, you can do it in Visios too. Yeah.
Yeah. For the Visio, if you make them on Visio, because obviously when we're drawing them out, the bigger is like bigger the better sort of thing.
Yeah.
Just for space. But for Visio, do you want us to print out on 11 by 17 or like?
You need to print them. Yeah.
But like,
yeah.
do you want it to be 11 by 17 or do you want it to be like just slightly bigger than 8.5 by?
No, print them out. If you're going to use Visio, or some people actually use AutoCAD P&ID because I think you can get a free license for that. I'm not sure how easy that is to use, but if you're going to print them out from CAD, print them out 11 by 17 because that's sort of the cheapest way to do it. If you want to print them out full size, you can, but you got to go to Staples to get that done. That's expensive. So I wouldn't really recommend that. Print them out 11 by 17. So don't print them out 8.5 by 11 because you can't read that. It's too small. Yeah, and then the paper we're going to give you guys is 17 by 22, so it's quite nice. That's not due. That is not due for Wednesday. No, no. Just if people want to get a jump on it. Yeah. Okay, so the only thing that might be missing on this P&ID that I'm thinking of right now is whether we need pumps down here or not. I think we've got the system designed so we don't need a pump down here, but it's close. It's close. Maybe what we'll do is when we get to the pump sizing, we might end up having to check that. So we might want to do the pump calculations just to check to see whether we can actually make the hydraulics work or not. Anything else I missed? Oh, okay, so like gauges and stuff like that. I would definitely have a gauge down in here. So I want to know what the material is that's coming off this tower. So I would definitely have a TI either on the bottom. I'd probably put it on the side. And we've got pressure. Oh, I should put a pressure gauge on here. There's a pressure gauge there. Any other questions? Just because if you want to, if you don't trust the PIT, you want to check the PIT, you got a pressure gauge there. Yeah. Yeah. I haven't put a manual valve underneath the relief valve, so that means the relief valve. We need to shut the system down to do maintenance on the relief valve. Any other questions? It looks like, when you look at it right now, it looks really scary, but if you start to just build it up step by step, it's not as scary looking. If somebody were to drop a P&ID like this on your desk, you know, the best way to go through it is to take a yellow marker and just start and just follow the major flows through and yellow stuff off and just go through it very methodically, almost like you were going to build the P&IDs, but you just follow it through. And don't get intimidated by the complexity of it right away. Just follow, find the major flows, find the major control loops, and then go back and look to see what other control loops are on there, or what other indicators. No more questions? Oh, electric tracing. That's what I had on there. Okay, so if you were worried about this stuff freezing, like the cooling water or something like that, then you would just draw a dashed line like this. You can put ET on it if you want.
Yeah, no, I'm saying that, yeah.
There, that's a way to show electric tracing on the P&ID. And because it's mostly methanol in this process, I wouldn't worry so much about stuff freezing. So only the cooling water. And that's actually another reason why an air cooler actually might be a good application here. You wouldn't have any electric tracing. That's all I got, you guys. Thanks for coming.